Now we know enough to define what is parametric approach in statistics, how to use parametric approach to describe your data. Well, let me remind you quickly what we have learned so far. So we know that what we observe can be summarized by calculating different frequencies, relative frequencies, real frequencies, the counts, the densities, and so on and so forth. While what is expected in future, we can define what is expected by computing different probabilities, right? So probability, it's expected frequency, theoretical expected frequency if we repeat our experiment infinite amount of times, right? So when we do the real analysis, when we analyze our real data, we can compute the different statistics, and we can also visualize these statistics. For example, we know that you can make a density distribution histogram, and you can make a percentage plot, right? So that shows you the percentage, the percentiles of your values, right? So this is densities of relative frequencies, and these are cumulative relative frequencies, right? For the future, for the theoretical expectations, we can find functions that describe this shape in theory. So for example, you got density distribution like this, but in theory, if your experiment meet certain requirements, you can have an expected shape, and this expected shape will look like a curve. Similarly, you can find the expected shape for the cumulative relative frequencies. Again, it will look like a curve. The difference is, here you have density of frequency, of relative frequency, and here you have cumulative relative frequencies. But when we talk about theoretical expectations, we talk about probabilities. So this is a probability, cumulative probability plot, and this is probability density plot. Okay. So the idea is, if we can find a function that describes the probability density or cumulative probability, and if this function can fit our data, our experimental data very well, we can use these functions to describe our sample. How we can do that? Any function depends on certain parameters. And what you need is actually to find these parameters. So you use your sample values to define parameters of these theoretical functions. So you kind of make a fit of your data with these functions. And then if this fit is good, then you use the parameters in order to describe your sample. For example, to compute intervals, to compute probabilities, to compute anything you want. So that's the idea of parametric approach. Fit your experimental data with theoretical functions. If this fit is good enough, by fitting, you compute parameters of this function, you estimate these parameters, and then you use parameters to do all the calculations, all the description of your sample. So this is it. So parametric approach is when you fit your data with a theoretical distribution function, estimate parameters of this function, and then use parameters, not data, but parameters, for computing intervals and computing probabilities. Okay. While parametric approach? Because usually you have functions with 1, 2, 3 parameters. And to estimate 1, 2, 3 parameters, you need at least, 4 data points or 5 data points. So you don't need a very big sample size in order to make a proper estimate of these parameters. So parametric approach can work well even if you have a small sample size. You remember, for non-parametric approach, we need bigger sample size, because non-parametric approach, it's based on these percentiles, the percentage values. And to calculate the percentage values, you need a lot of data points. In this case, you don't, because if you have 2 parameters, 3, 4, 5 points will be enough to make an estimation of these parameters. That's the advantage of the parametric approach. Probably this sounds a little bit vague and a little bit abstract so far, but in the next video, I'll show you an example how to use parametric approach using one of the simplest theoretical distribution, which is called a uniform distribution.